I will first apologize to some of you who were there in July at the conference in Politecnico di Torino. That's going to be very the same talk. I'm sorry for that. So I will start by introducing what's a Becker-Döring model. So that's a particular kind of coagulation fragmentation model, which is a particular kind of chemical reaction network. So our chemical reaction network is the following. So we deal with species that have a size. The size is a number of elementary particles or monomers they contain. So the Ci is a cluster or polymer of size I. The C1 is a cluster of size 1. So that's one monomer, one single particle, one elementary particle. And when they meet together, they form a particle of size I plus 1. So the monomer binds to the cluster of size I to make a cluster of size I plus 1 with a given rate that depends on the size of the aggregates. And the reverse reaction is a polymer of size I plus 1 may release one by one a single particle to make a monomer and a cluster of size I at a given rate given by B, which may also depend by to the size I. So writing like this as a system of ordinary differential equation, you actually have an infinite number of reactions. So strictly as being infinite dimensional, it may not be called a chemical reaction network. You have an infinite number of ordinary differential equation where each term in the right-hand side is drawn by the law of mass action, the standard way we could transfer a chemical reaction network into a deterministic system. With the particular thing that we have a conservation law, which is the total number of particles in our system. So that's sum of ICI. Recapitulate the number of particles, the total number of particles, either being in monomer or in aggregates. And this quantity has to be conserved because each elementary reaction does conserve this quantity. And so for each aggregate of size I, it's involved in 4 reactions. And when we group them 2 by 2, we have a difference of flux, and the flux is called GI. And the first elementary particle is very particular because it's involved in all reactions, either as a product or as a reactant. And then all in the right-hand side has all the flux in its right-hand side. So as it is, it's an infinite dimensional system of ODEs. So already the well-posedness of the system is not completely trivial, and we'll come back to this in a minute. But if we want to interpret this model as a stochastic model, as a continuous Markov chain, we are now going to deal with integer numbers of aggregates. And as we will discuss with integer number of aggregates, we'll have a finite numbers of particles. And because we'll have a finite number of particles, there will be a maximal size allowed in the system given by this total quantity at the initial condition. And then the number of reactions become finite, and it's a proper chemical reaction network. So the transitions are the following. So you lose one particle, one aggregate of size I, and you gain one particle of size I plus 1 for the aggregation. And then for the fragmentation is a reverse reaction. And later in the talk, we will interpret the size of the particle as they undergo some kind of random walk in the size space. So they do jump one by one in the size. Each aggregate can increase or decrease its size one by one. A little bit of motivation. So this kind of model are typically used in physics to understand some properties of materials or fluid. And we typically have some guess of the functional shape of the coefficient, which are the key 3 parameters in our model. So the network is fixed, but we have this freedom of choice with the parameter A and B, which depend on the size. And the exact way how they depend on the size depend on physics law, and in particular, it's often used Laplace law for the pressure. It will depend inversely of the radius of each bubble or each aggregate as depicted here. And then the exact form, the exact shape of the coefficient will depend if you are in a solution which is reaction limited or diffusion limited, or will depend on the dimension of your system and so on and so forth. I won't go into these details. I assume the coefficients are given. I have typically this functional shape in mind, but they can be different. And I assume they are given, and then I want to know what's the property of the mathematical model once I have prescribed the parameters. And just for this shape of coefficient, a particular feature is that for small size of coefficient, and if you tune the parameter which appears here, the Q and the ZS, For small size, you may have the fragmentation, so the B, which is bigger than the A. Then for large size of clusters, the A may become above the B, and the coagulation may become favorable with respect to the fragmentation. This will be important in the next. And we have typically a threshold where all size below this threshold tend to shrink, and all size above this threshold, depicted here N star, will tend to aggregate and become larger and larger. A few last motivations. So this model is a classical model for nucleations in as I say, in material physics, but it's also more and more used in biology. It believes that this property of nucleation and fast separation, which I will come back to, is heavily used by intracellular mechanisms, which may be a mechanisms to phase segregate some of the protein inside cells. And it's also occurring in cavity formation, for instance, in the embryo, where you have small droplets initially appearing, and then one big cavity emerge through a mechanism that is believed to be similar than nucleation in physics. So some of the theoretical questions we ask on this model is when does the nucleation process take place? So when, with respect to the coefficient A and B, for which choice of coefficient A and B do we have nucleation? So I will have to come back of how we interpret nucleation in this model. If it occurs, how long and how variable in time this period can take. And once nucleation has occurred, how fast the big cluster emerge. And some more theoretical or mathematical question are, is the model well posed? So as I say, it's an infinite dimensional model, so that's not trivial. What are the long-time behavior? What is the equilibrium or steady state? What is convergence speeds toward equilibrium? And do we have non-equilibrium interesting property? And it will be much about this today. It will be about the equilibrium property of the model and some of the metastability phenomena of this model. So I start with what is known in the literature since 1986 and this seminal paper from Balkar and Pelrose on the deterministic version of the model. So once again, it's an infinite dimensional model. Sorry. So well-posedness theory has been drawn by these guys. Essentially, what you need to ensure is that the well-posedness, the mass conservation makes sense, so that the C1 and the sum of ICI makes sense for all times. And to make it short, the biggest constraint, or the easiest one, actually, you can say that both AI and BI are sublinear for large size. If you can just stick to this condition. If both AI and BI are sublinear in size, then everything here makes sense. And as long as you start with a suitable initial condition, the solution is well posed and unique for all times. Then we ask, what about steady states? And the first thing you may do when you look for steady state is looking for solution to the right-hand side is equal to 0. And writing like this, you quickly realize that all the flux has to be equal. And then because of the equation on C1, they actually have to be equal to 0. And then if you look a solution that make all the flux becoming 0, you have this family of solution. They have to look like this. Qi is a parameter, so it's a function of A and B. Z is free for now. We're going to see how we can fix it. And Z to the I. So that's a family of solution indexed by Z. And you see here for the C1 is still free because Q1 is 1. And so that's actually C1 is Z. So knowing Z is knowing C1. And if you know C1, you know all of the Ci at equilibrium. So this was calculated by looking at the right-hand side equal to 0 for the ODE. And we remember that we know for all time the system preserves mass, that is the sum of ICI here. So it's natural to look for an equilibrium that also has the same mass, the same sum of ICI. So you plug this candidate, this family of candidates, into the mass conservation, and you look for a solution such that the sum of IQI ZI, so the mass of the potential equilibrium, equal the mass of the initial condition. That's a natural question. And things get complicated when you realize that F, so my function F here, is actually a power series and may not be bijective on the half line. So there are some cases where it's bijective, but we also have cases where it has a maximal value. So you may have a finite radius of convergence and a finite limit at this radius of convergence. So once again, for specific choice of coefficient A and B, which are believed to be interesting for physics, and typically the power law AI I to the alpha, where alpha is between 0 and 1, will typically produce this kind of shape. So we have a finite maximal value for this function. If you start above that value, then there is no equilibrium. If you start with choose an initial mass above the critical mass, in the third case here depicted bottom left, you start above, there is no equilibrium that have the same mass. So the natural question is what's going on in this case. So we stick to this case. So we assume we have A and B coefficients that such that we have a finite value, and we look for critical mass. We look for initial conditions that are above the critical mass. And the theorem, so again, back to the 86, is the following. If you start with sub-critical mass, so we should start with the initial condition, which are the sum of ICI, so mass strictly lower than lower or equal, sorry, the critical one. Then you have strong convergence in a strong topology, the small L1 topology you can do on this state space. So everything is nice. And if you have a supercritical solution, then you only will converge to one of the candidates, but a candidate that have a strictly lower mass and actually the closest in a sense. So the critical one, which has the mass rho s, which is the maximal allowed in the system. And this loss of mass, so the initial condition has a mass strictly higher than the steady state. So there is a loss of mass occurring at time infinity, is interpreted as a nucleation, meaning that the loss of mass is going somewhere else in a different phase. And so it's interpreted as a phase transition. Some of the material has nucleated and leaves the initial phase. A quick comment on how we prove this kind of theorem. And we actually can, so we are saved here because we have most of the properties of detailed balance, finite dimension chemical reaction network. And in particular, we have this Lyapunov function, which is very helpful. But because we are in infinite dimensions, some of the continuity property of the Lyapunov function are not trivial. And actually, for supercritical condition, we have no continuity property in strong norm. So we have to work in a weak topology and work a little bit. But in a sense, the trajectory will minimize the Lyapunov function and converge to the unique minimizer of the Lyapunov function, although it will be in a weaker topology than the one we would originally have chosen in a finite dimensional chemical reaction network. Okay, so now I will switch to my work. So we got interested in the stochastic counterpart of this model. So I recall how you could write it down as a Poisson-driven stochastic differential equation or as a continuous time Markov chain. That's the same model. So we have the same transition, same notation, nothing has changed. And we work now in a finite state space where the small n here is fixed. We could do something else, but here small n is fixed, is deterministic, is given. So we have a maximal size and everything is finite. The number of reactions is finite. The number of state space as well. As I said, we are actually in a case with a reversible detailed balance system. So once again, we are back to the chemical reaction network world, complex balance or even detailed balance. We have an equilibrium, which is a product of Poisson law, and it satisfies the detailed balance property of a continuous time Markov chain. So the interesting part is not there. We know it will converge. So the initial condition on the continuous time Markov chain will converge to the equilibrium steady states. But we now ask what's going on if n, the small n, which was fixed, tends to infinity now. So we see it as a parameter, and we want to see what's going on when n goes to infinity. So for each finite n, everything is known, but the limit when n goes to infinity is open. So for that, we have to rescale the model, and we do the classical large volume scaling. So n will play the role of the volume here, and rho, which has the same meaning as before, but will have the meaning of the density. So my number of particles will be n over rho. And so I'm now in a state space, still finite for each n, but with all have renormalized, all condition has a finite density, and I increase the volume. By doing increasing the volume, I'm increasing the number of particles as well. And I rescale the reaction rate so that they all scale with n, and the transition all scale with 1 over n as a classical large volume scaling. So we know that everything should converge to an ODE in the finite dimension case. And it is also the case here. It's slightly more complicated because, again, we are infinite dimension. But with some work, we can work on it and show that we converge to the ODE. And we now ask what's going on to the stationary state, so my stationary distribution. And once again, we started from a more or less recent work from David Anderson and co-authors that relates for complex balance stochastic reaction network, relates the distribution or the logarithm of the distribution with the entropy, with the Lyapunov function. And we were also here surprised to see that we have the same relation that holds. So if we rescaled the stationary distribution of the continuous Markov chain, for subcritical case, we recover the Lyapunov function in a strong norm. And not surprisingly, once we know the result in the deterministic case, if you start with a supercritical solution, we also recover the Lyapunov, but the one that is helpful for the deterministic case, so the one which is at the critical value. And it proves, in particular as a corollary, that the probability distribution as n goes to infinity will charge density which has larger and larger aggregates, which will not be seen by the weak star topology, because this distribution will charge only density of size rho s or finite size, and meaning that there is something going on and there is some clusters going at size infinity, which is captured by this limit. So a quick word on the method of proof. We exactly follow the method of proof of David Anderson and co-authors from 2015. We write down the explicit, so we have the explicit form of the stationary distribution, so we can calculate this. Everything is in exact calculation here, and it's just a matter of making some term appear and some of the algebraic calculation, and using continuity property because we are in infinite dimension. It's not completely trivial that the Lyapunov function is going to be continuous or not. Will depend on the topology, and but the same spirit of the proof can be followed to achieve this result. So we have one missing result we would like to prove here, is that what's going on to the part that diverge plus infinity. So I told you that we know by this limit that some of the cluster has infinite size at the limit n goes to infinity. We don't know how much and what is the typical size of it. And by numerical simulation, we conjecture, at least in some cases, that we have a single giant clusters of that size, which is a missing part when you compare the critical stationary and the initial condition. So we have one giant cluster of that size. All the remaining one have a finite size with respect to n. So that's still a conjecture. We'd like to prove it, and there are certainly other fields that could help on that. Okay, and to the last 5 minutes, I will quickly speak about what we can say on non-equilibrium dynamic. So before reaching steady states, again, we started from what is known on the deterministic theory. Some of the results are the following. If in a supercritical solution, we can stick to the numerical simulation here. The different lines are not important. It's how you can simulate it accurately or not. But the general picture is the following. Starting from some initial condition, you will spend a very long time, but a finite time, but a very long time in some states, which is not the final steady state. And you can quantify this precisely for some of the initial conditions, not everything. And the conjecture is that actually that state, that intermediate state, is attractive in some sense. It attracts many initial conditions. That's stays there for a while before converging to the fully stationary state. And I have to say that this meaning of being so long time or not is with respect to a small parameter, which is the difference between the supercritical density and the critical one. So if you are just above the critical density, you will have this metastability phenomena. And this is what we see in a numerical simulation, numerical trajectories of the stochastic model. So in color, it's one simulation, and in black, it's averages of a few of them. And you typically see, no matter which output we calculate or we plot in this figure, we typically see that the number of given species or their mass or the number of polymers will spend a while, so in a log scale in time, in some states before reaching the stationary state. And if we decrease the supercritical density, it will get larger and larger. And interestingly, the time where this transition occurs from the metastable states to the stationary one is concomitant to the formation of one giant clusters, which here is the plotting in red. The maximal size in the system was below 10 before that transition, and reached suddenly with 300, which given the total number of cluster particles is huge here. Okay, we wanted to have a theorem that could quantify a bit this. It turns out that in full generality, we are still not able to do it. But in a modification of this model, we can have precise results, and we believe they reflect what's going on in the original model. So I will cheat now. I will assume the total number of single particle, my C1, is constant. So while doing this, I break everything. I break the mass conservation. There is no more mass conservation, actually, when I'm doing this. So I'm assuming I'm in excess of monomer in my system, and each of the clusters that appears behave actually independently of each other, doing, as I said in the introduction, some burst and death plus and minus one in the size state space. And it turns out that for the choice of A and B that produce this phase transition mechanisms, they match exactly with what is known with one-dimensional burst and death processes, meaning that there is a notion of a transition for a small z below some critical value. The burst and death process is subcritical and will come back to the left, will come back to one almost surely. But above the critical value for the Z, for the number of monomers, which is above that ZS, there is a supercritical burst and death where it may not reach one, but will diverge to plus infinity with some probability. And this is, we can go a little bit further by looking at the number of clusters given some given size. And we make it short here, but we can calculate in this setting everything. We can calculate a quasi-stationary distribution explicitly, which interestingly also have a product form. And that quasi-stationary distribution will quantify the metastable state and will attract all initial conditions, given that you haven't formed a critical cluster of size bigger than n. Okay. And we can get a bit more precise. We can have convergence rate towards this quasi-stationary distribution. And because we have explicit or at least estimate on this convergence rate, we can say exactly in which case the time you will converge to the quasi-stationary distribution is faster than the time you will converge to the stationary state. So everything is explicit in this formula. It's a complicated formula, but everything is explicit. And it will quantify the two-time scale going through the quasi-stationary distribution state, the metastability, or going through the true equilibrium. And we like to have a similar result in the full original model, but we are not yet there. I will go back directly to the numerics and the conclusion. So once again, we have this numerical simulation where we can quantify many things and observe many things. I was in a strictly supercritical case, so the initial density was higher than the critical density. And if I increase, if I look a little bit different, my simulation, I could plot here the size distribution at any given time. So again, in blue, it's one simulation, and in black, it's some average. And I use a log scale for the size distribution, because I know I will have a lot of small clusters, but very few large clusters. And actually here 10 to the 0 is 1. I indeed have one giant superclusters. I have renormalized the size by n, so they all fit to 0 and 1. I have one giant clusters that emerge at some particular time, and it seems to be stable, and there is not a second one in this simulation. And we can also look at how the relative entropy behave with respect to the time trajectory. And maybe not surprisingly for those who are familiar of numerical system, we see that the relative entropy seems to plateau exactly at the period of the metastability. So there's not much change in the relative entropy. And at the transition, where you form this large cluster, you have a sudden drop in the Lyapunov for the relative entropy value. And to conclude, few open questions. So for the original system, we are interested in looking at how many supercritical clusters, which we can precisely define, appears in the system. Are they transient or do they persist in the stationary states? So do we have a situation where many large clusters can occur? And if they don't, how long it takes for a single one cluster to win the competition with respect to the other? And with that, I thank you very much. I will thank my collaborators, Juan Calvo, working at Granada University, and Erwan HINGANT at Amiens University, and Julien Deschamps, a former collaborator. Thank you very much.